Hello and welcome to another chemistry video. Today we're going to talk about periodic trends and a little bit about the table organization. After completing this video, you'll be able to compare periodic trends such as atomic radii, ionization energy, electronegativity, etc., and state the reasons for these variations. Okay, first let's talk a little bit about some of the groups or elements that are put together for having common characteristics. The group 1 elements, alkali metals, they're all silvery in appearance. They're all soft enough to cut with a knife. None of them are found in nature as a free element because they're very reactive. They'll always be combined with another element. You won't walk down a trail and trip over a chunk of lithium. As you go down the periodic table, their melting temperatures get lower, so they melt easier. They're extremely reactive when you add them to an aqueous solution. In other words, when you put them in water, they're going to produce hydrogen, which is kind of cool if you see it. And hydrogen, just while we're on it, is not included as an alkali metal. Now, I said these look kind of cool as you're going down the periodic table. Now, at the bottom of this slide, there's a web address to a video that's unfortunately not on YouTube, but it's kind of cool. They go through each one of these elements going down the table, and you can see how each one is a little bit more reactive than the one before it. Kind of interesting to watch. You might want to check it out. Okay, our next group 2 elements. They're alkaline earth metals. They're harder, denser, and stronger than alkali metals. They have higher melting temperatures than alkali earth metals, yet they are still too reactive to be found as free elements in nature. You, again, won't walk down a trail and trip over a chunk of magnesium in your path. Let's talk about transition metals next. They are group 3 through group 12. Those are all the D block elements. They're right in the center of the periodic table. They are excellent conductors of electricity and actually heat too, for that matter. They have a very high luster, or kind of shiny. They're always absorbing and emitting photons at about the same frequency. It makes them look very shiny. They're less reactive than alkaline earth metals or alkali metals, and some of them actually do exist as free elements in nature. If you're lucky enough to, you may be walking along down a trail and trip over a chunk of silver or a chunk of gold, in which case you wouldn't really have any need to finish a chemistry course. You'd be well off enough. At the bottom, I have a link to a good website that has a periodic table of clickable links, and you can learn about a lot about each and every element that you click on in this periodic table. It'll show you what they look like, their boiling, melting points, electron configuration, lots of interesting little tidbits that might help you out as you're taking a chemistry course. Next up, we have a few other groups. You may hear the term main group elements. This refers to the S and the P block, but it excludes hydrogen and helium. So we're talking about groups 1 and 2, the S block, and then groups 13 through 18, the P block. Okay, P block elements consist, they're very diverse. They consist of nonmetals, metalloids, sometimes called semiconductors, and metals. At room temperature, these can range anywhere from gases to liquids to solids, so very diverse group. Okay, halogens, which are in the P block, that's group 17 elements. Up at the top, the very first one is fluorine. And these are very reactive, and they commonly bond with metals to form salts. So it's pretty common to see one of these bond with something clear across the table. So sodium chloride is a great example, table salt. Okay, our last one on here, noble gases. These are all the elements that are in group 18. They're all gases. They are the least reactive of all elements. because the vast majority of them have 8 electrons in their outer layer, helium being the exception, only 2. But regardless of which one it is, all of them have their outer layer of electrons, their valence layer is full. So they generally don't want to react with other elements. Here's the first of our trends, periodic trends, the atomic radius. You would think that finding the radius of something that appears round would be relatively simple. You just measure from the center to the outside edge, just like any circle. Well, the problem arises in that the outside of this circle, the outside of an atom, is kind of fuzzy and indistinct because it's the outside of an electron cloud. So the way that atomic radius is determined is 2 atoms of the same element are bonded together, and then the measure from one nucleus to the other is taken, and that is then divided in half and called the atomic radius. Okay, factors that affect atomic radius, and to be honest, every single trend we're going to talk about, nuclear charge, increasing number of protons, repulsion of electrons from one another, they all have the same charge, don't want to be near each other, and the distance of electrons from the nucleus. So let's apply this to atomic radii. The atomic radii gets smaller going across a period from left to right. This is caused by increasing positive charge of the nucleus. In other words, you add more protons, more positive charge, it has a stronger pull on the electrons, pulls them in closer. There, of course, is an exception. The first electron in a p block that is following a d block element, those actually jump a little bit. They get a little bit bigger, and then they start getting smaller again as we go across the p block. Okay, group trends. In general, the atomic radii of main group elements increases as you go down. And all of these little diagrams that I've drawn here, I have my arrows pointing in the direction that these trends increase. Some people have them drawn one way increases, another way decreases, and that gets a bit confusing. So on all of the ones I have drawn here, wherever the arrows point, that's an increase in the trend. Ionization energy, our next trend. It's the amount of energy that must be added to an atom when it's in the gas phase to remove an electron from the atom. This relates back to the Bohr model. A photon comes along, strikes an electron. The electron jumps to a higher energy level. Well, if it's enough energy, that electron can actually leave the atom. Okay, period trends. In general, ionization energies in main group elements, they'll increase from left to right. And that's caused, again, by adding more protons, nuclear charge increase. Group trends, as you go down main group elements, the electrons get farther from the nucleus and more electrons are there to repel one another, so we have a decrease in the amount of energy it takes to remove an electron, because the farther they are from the nucleus, it's like two magnets. The farther apart they get, the less pull they have on one another. Okay, the last point I have on here, it is possible to remove more than one electron, but the more electrons you remove, ionization energy 2 requires more energy than removing the first electron. Ionization energy 3 requires more energy than removing the second electron, and so on. You generally don't see 4, it could happen, but it's not very common. And here we have our diagram for ionization energy. Again, arrows pointing at what increases. A few definitions here for you. An ion is an atom with a charge on it. And there are 2 types of ions. There are cations, atoms that are positively charged. They've lost at least 1 electron, so they have more protons than electrons, making them positively charged. And anions, negatively charged, because they've gained at least 1 electron, so 1 or more electrons than the number of protons. And as I said before, metals at the left tend to form cations, and nonmetals at the upper right tend to form anions, and they will bond together. And noble gases, again, they remain neutral, so you're not going to find ions here. Electron affinity. This is really the exact opposite of ionization energy. How likely is an atom to pick up an electron? the energy change that occurs when they pick up electrons, atoms do. Most of them are going to release energy when they acquire an electron. Period trends. Group 17 is the most likely group out of all of them to absorb electrons. Group 16 is the next most likely. Group 15 can still pick up electrons. Group 17 most likely. So group trends. Generally, it's more difficult for elements to acquire electrons going down a group. Again, we've got a lot of electrons shielding the nucleus, and so we've got all this negative charge on the outside of an atom, and another electron trying to find its way in is going to be pushed away. Our last trend we're going to discuss here, electronegativity. It's a measure of how strongly one atom will attract the electrons of another atom when they're in the same compound. Now, fluorine is randomly given the value of 4, and all elements are compared to it. 4 is the absolute highest electronegative value. So period trends are all going to increase going toward fluorine up here in this top right corner. So going up the table, up a group, the electronegativity increases, and going across from left to right, electronegativity also increases. Okay, that's it for this video. Hope that helps you out.